This is Jack Jackson. In our last video, we stated and proved L'Hopital's rule, and L'Hopital's rule is used to find the limits of certain functions where they are the form 0 over 0 or infinity over infinity. In this video, we're going to work out 4 example problems where the form is the indeterminate form 0 over 0. So what I'd like you to do on these is, like I always like to do on my videos, when I give you a problem, I'd like you to try to work it out yourself. And then as you work it out, get it done, you'll press pause in the video to do that, and then come back and check your work. So let's just review L'Hopital's rule real fast before we go on. So L'Hopital's rule says if f and g are differentiable functions on an open interval I containing some number a, and the derivative is not 0 there for g, but we don't really care what happens at x equals a, then if the limit is x approaches a of f of x equals 0 and limit of x approaches a of g of x is 0, so that has the form 0 over 0, or perhaps the limit is x approaches a of f of x is either positive or negative infinity, and the limit is x approaches a of g of x is positive or negative infinity, so then it has the form plus or minus infinity over infinity, then we can apply L'Hopital's rule, and the conclusion is that the limit as x approaches a of f of x over g of x is the limit as x approaches a of f prime of x over g prime of x. And that's going to apply to the 4 examples that we're going to do here. So here's the problem I'd like you to try to work out, and you're going to use L'Hopital's rule. So compute the limit as x approaches 0 of 1 minus e to the x over x. Press pause now. Well, first of all, we got to make sure that L'Hopital's rule applies. First of all, we take the limit of the numerator, 1 minus e to the x, separately as x goes to 0. So as this goes to 0, this goes to e to 0, which is 1. And then you have 1 minus 1 is 0, so that limit is 0. And certainly the limit as x goes to 0 of x is 0 as well. So it has a form 0 over 0, and both the numerator and denominator as separate functions are differentiable functions. So L'Hopital's rule has the hypothesis of L'Hopital's rule is satisfied, and so we can apply it. So the conclusion is this limit that we have here we can find by taking the limit of the derivative of the top over the derivative of the bottom. Now let's do the easy part first. The derivative of x with respect to x is just 1. And in the top, say the derivative of 1 is 0, and the derivative minus e to the x is minus e to the x. So that function, after we've done the derivatives, simplifies to the opposite of e to the x. And now we take the limit as x goes to 0. This goes to minus e to the 0. E to the 0 is 1. Then negative out front makes it negative 1. And so we see that L'Hopital's rule is going to tell us that this limit is negative 1. And we can sort of corroborate that by looking at a graph. And sure enough, this is the appropriate portion, at least, of the graph. And sure enough, you see as x goes to 0, y goes to negative 1. You can see that hole in the graph right there at 0, negative 1. And of course, in this particular case, the function is undefined at 0. It's the form 0 over 0, of course. Now, how about another example? So this one is actually not just one example, but a whole family of examples. Compute the limit as x goes to 0 of sine of ax over sine of bx, where a and b are any real number constants. Okay, so see if you can work this one out. When you get finished, come back and check your work. Press pause now. Well, first, again, we need to make sure the techniques work. Now, actually, we've actually done this same limit earlier using some different techniques, using one of those basic special limit formulas that we did. Sine of u over u as u goes to 0 is 1. Using that limit property and a little bit of manipulation with some algebra, we were able to work this limit out earlier. But we're going to use a different technique here, and we'll get the same result, of course. So when you consider the numerator and denominator as individual functions, they are certainly differentiable functions, actually everywhere. And if you take the limit as x goes to 0, they're both, again, they're not only differentiable functions, that makes them continuous. So you just plug in x is 0, and a times 0 or b times 0, either way is 0, and so you get sine of 0 is 0, and so you get 0 over 0. So that's the form we have. And that is exactly when you can apply L'Hopital's rule. So we take the limit of the derivative of the numerator divided by the derivative of the denominator. So you take the derivative of the numerator and denominator separately. This is not the quotient rule. This is something different. Okay? So the derivative sine of ax is cosine of ax times the derivative of the ax, which is the a. And similarly, the derivative of sine of bx is cosine of bx times the derivative of bx, which is b. Now, when we take the limit as a goes to 0, these are continuous. The whole thing's a continuous function now, so we can just plug in 0. A times 0 is 0, cosine of 0 is 1, so the numerator is a. And similarly, b times 0 is 0, cosine of 0 is 1, times b is b for the denominator. And so this limit turns out to be just a over b. And I'm going to illustrate it. Of course, to illustrate this, I'm going to have to pick a specific value for a and b. In this case, I picked a equals 7 and b equals 5. So the limit should be 7/5, which is 1.4. And sure enough, here, some funny things going on with this graph. You know, you got some, here's a piece that's got some vertical asymptotes. It's decreasing, and then, you know, an inflection point in here, and then there's a little piece that's concave up with some vertical asymptotes, and this little piece is increasing, and so forth. But if you notice, it's undefined at x equals 0, but it has a hole in the graph. And sure enough, there it is, right there at 0, 1.4. So 7/5 is our limit. All right, compute the limit as x goes to 0 of x squared over 1 minus cosine x. Now again, we may have done this one with some other techniques earlier, but let's use L'Hopital's rule this time. Go ahead and work this out for yourself. Press pause now. Well, we see again that it is something we can use L'Hopital's rule on it. The numerator and denominator are actually differentiable functions everywhere, certainly near x equals 0. And as x goes to 0, of course, 0 squared is 0. Cosine of 0 is 1, 1 minus 1 is 0, so we get the form 0 over 0. That is, again, exactly one of the two cases where we can actually apply L'Hopital's rule. So, L'Hopital's rule says then this limit is the limit of the derivative of the top over the derivative of the bottom. Alright, let's see. The derivative of x squared is 2x. Derivative of 1 is 0. Derivative of cosine is the opposite of sine of x, so that turns that minus into plus. And so we have 2x over sine of x. Again, we could use a rule. Actually, we already know that the limit as x goes to 0 of x over sine x is 1. So this answer should be just 2. But if we didn't remember that, we could use L'Hopital's rule again. So the derivative of the top is the derivative of 2x is 2, and the derivative of the bottom, derivative of sine x, is cosine x. L'Hopital's rule applies because we're still in the form 0 over 0. Right? 2 times 0 is 0, sine of 0 is 0. Okay? They're again continuous functions, actually differentiable functions even, everywhere. So certainly we can, when we consider it as separate functions, they're differentiable everywhere. And so we can consider this L'Hopital's rule appropriate, and so we did that here. Now we can actually plug in the 0 here and get 2 over cosine of 0. Cosine of 0 is 1. 2 divided by 1 is 2. And so we should see a hole in the graph at 0, 2. Now when I graphed it in Graphmatica this time, the hole didn't show up as a hole, but it actually is. If you look at the table, you see right here where it says 0 error. And so in fact it does show up sort of as a hole there when you look at the graph in conjunction with the table. So you see the hole there. And a lot of times on your graphing calculator, you'll have that kind of a setup. You won't really see the hole in the graph, but you can see that there's a point missing there when you look at the that part of the table. All right, let's do one more here. The limit as t approaches 0 of sine of t over e to the 3t minus 1. Okay, see if you can work this limit out now. Now that you've seen a few examples, you definitely should be able to do this one on your own. So work this out now, please. Press pause. Okay, first of all, we need to make sure that we can apply L'Hopital's rule. Okay, the top and bottom as separate functions are differentiable functions again. We know about these functions. So we know that they're differentiable. And they both approach 0. Once again, sine of 0 is 0. 3 times 0 is 0. E to the 0 is 1. 1 minus 1 is 0. So it says the form 0 over 0. So we may apply L'Hopital's rule, which says we get the same limit if we just take the derivative of the numerator and the derivative of the denominator separately. So the derivative of the numerator, derivative of sine t, is cosine of t. And the derivative of the denominator is, so the derivative of 1 is 0. This is e to the u, so it's e to the u times derivative of the u, which is 3t. And this should be the derivative with respect to t. So let me get that typo fixed. There we go. All right, well now we can actually plug in 0 because what we have left here is a continuous function. Cosine of 0 is 1. 3 times 0 is 0. E to the 0 is 1. 1 times 3 is 3. So we get a 1 in the numerator, 3 in the denominator. That is 1/3. And so this tells us the point 0, 1/3 should be a hole in the graph. And sure enough, right there it is. So if I zoomed in kind of close here on a portion of the graph, we see that. Now, I think we're going to stop there. In the next video, we'll come back and do some more L'Hopital's rule problems. But this time, they'll be of the form either plus or minus infinity over infinity rather than 0 over 0. And of course, L'Hopital's rule applies in that case as well.